than 0.80.
Mm-hmm.
I'll be honest with you, got no idea how to figure that out.
So this is one in which I'm asking you to refer to the spreadsheet that I included along with the data file. One of the tabs inside that spreadsheet is a reliability and information. Let me see if I can pull that up real quick here and get that available for reference. One moment. Okay, yeah, so there's an Excel spreadsheet called binary ML underscore plots that because some of the versions of M plus across operating systems don't make pictures or don't make the same pictures, I added that. So there is a tab in here called binary test information that you would need to refer to answer that question. And what this tab is giving you is the amount of information that the items contain at a corresponding level of the latent trait. So in this picture, the y-axis is information and the x-axis is theta. So I said of the traits given, meaning one of the ones that's in this table, and then what was the rest of the question?
Sorry, I had to bring it up again. It is, oh, so many things on my screen. Hold on. The smallest trait value for which the predicted reliability is greater than 80 or
Okay.
0.8, sorry.
Okay. So what I'm looking for you to be able to do is to convert this test information curve into a reliability curve. And then you will have the corresponding theta at which it hits the cutoff of 0.8, 0.9. There's 2 or 3 questions that are asking about the same idea. So information divided by information plus 1 gives you reliability in a metric that normal people will know what it means, whereas test information is a metric that most people will be unfamiliar with. Okay. Any other homework questions while I'm on the topic? Okay, then as promised, we had Halloween last weekend. Wanted to give you Huey Claws.
My goodness.
So, Merry Halloween, everyone. And yeah, that giant beard lasted about 10 seconds. He said it was very itchy and he wanted nothing to do with it, but the outfit was fun. So, surprisingly, he was not too disappointed about not being able to go trick or treating. They did a trick or treat activity at his school, and we made a scavenger hunt for the house where he had to go find candy, and that seemed to be fun. So, Merry Halloween to all of us. Homework question, or a general question. Let me see here. When we run CFA and IFA, is the difference in item scales, different response choices among the items within one factor not a problem? Is it right that we don't need to standardize the items? I'm not sure what that question is asking me. I can tell you that the difference between the models, CFA posits a linear relationship of the trait in directly predicting the item responses, which implies that the item response distribution is continuous, whereas an IFA model is an ordinal model that has a series of binary submodels that constrain the predicted probability of each submodel to range between 0 and 1. And so the net result of the binary submodels, each of which has those constraints, is that the predicted item responses don't go past the boundaries in which they are, and there is a predicted value for each separate integer. So there's nothing that's in between. Correlation. For example, a factor consists of five response item scale and 6 response items. Oh, okay. Whether or not, so I think you're asking, is it okay to have some items that have only 5 response options and some items that have 6 response options? Correct. Okay, yes, I understood the question. I am killing it today. Yes, that is okay. The differences in the number of possibilities would show up as differences in the item parameters. So an item that has 6 choices might have a higher intercept, for instance, because there's more room for the item to vary. But so long as each item gets its own item parameters, its own item intercept, its own loading, and its own error variance in a CFA framework, then there's no problem with having different numbers of responses. That could happen anyway. You could have a scale where all of the items have, say, 5 possibilities, and for some of the items, people don't pick one of the options. So that item functionally becomes a 4 option item. That's fine. We only run into problems with differences in item format if you're going to fit an ASU model, an add shit up model, right? Then items that have more variance are going to be weighted more heavily in the sum, but we're not doing that, so we don't have to worry about it. All right, other questions? Okay, so I'm trying a new thing. The recording thing has been weird with my computer. That's why I've shut off the background and I'm only recording and not streaming. So I'm hoping to be able to eliminate all the reasons why the video is not syncing with the audio. But I'm going to continue to try and narrate whatever I'm doing in case that happens again. So please bear with all the technical difficulties. I'm trying to make it work. That is the theme of this semester, right? Like Project One Runway. We're just going to make it work. That's what we're going to do. All right, other questions before we dive back into stuff? No? All right, want to talk about ordinal models then? What do you remember about ordinal models? We started talking about those last time. Anything? I've got slide 6 in lecture 6 here to try and trigger your memory. We have a new vocabulary word, polytomous. That means categorical in IRT terminology. What do you remember about these models? Anything? Binary submodels? Yeah. So all of the models that for categorical data, all of them use a multinomial response distribution. They differ from each other in how they phrase the binary submodels that it takes to distinguish all of the categories. C minus 1, yeah, that's the number of binary submodels that you need. Proportional odds is another one, yeah. So the graded response model, the one that's the most common that assumes ordering of the response options, is otherwise known as a proportional odds model, which means that the slopes are constrained to be the same across the binary submodels. That is also true. What else? Should we go back over it then? Would that be good? There's some smiles. Yes. An enthusiastic yes. All right. Picking up on slide 6 then, let us revisit all of this stuff. All right. So we're going over simultaneously both the IRT parameterizations of these models and the IFA parameterizations of these models. Let me move this thingy out of the way. So the difference, IRT is going to phrase these things in terms of A's and B-like parameters, so discriminations for the slopes and some kind of location that gives you the trait level at which something happens. What that something is going to differ across models. Whereas IFA, item factor analysis, phrases the same models in terms of loadings for the slopes, so factor loadings like in CFA, as well as thresholds. So the opposite of an intercept, it gives you the logit of the lower category when theta is 0. So I'm giving you both versions of these. You can work back and forth across the two. What you get out of your software depends on what package you're using, which is why I want you to be familiar with all of the different permutations. So there are 3 main types of models for categorical data, and they differ in whether or not the response options are thought to be ordered. So if you know for sure that the response options are ordered, so in Likert scale data, and by the way, it is Likert, it's a person's name as it's known, like strongly agree, agree, neutral, disagree. How often do you do this? Rarely, sometimes, often, like anything like that, where the answers are unambiguously ordered. We can fit what's known as a graded response model. That is also known as a cumulative logit model or proportional odds model. in non-latent trait versions of these things. If you're not sure if all of the responses are ordered, you can fit what's known as a partial credit model, and that is an adjacent category link. Those are less common, but they tend to be used more often by Roche people because the partial credit model is a Roche model. By default, it has the same slope across items. If you want to let the slopes vary, that becomes a generalized partial credit model instead. And the last one, if your response options are not ordered. So if you had to say, for instance, something bad happens, which of the following reactions would you be most likely to have? Something like that where you're picking. Or if you had to say, what's your favorite ice cream flavor or your favorite pet or something like that, where you might think there's an order, but somebody else might disagree with you as to what the order is. Those all would fall under what is known as a nominal model or a baseline category logit. So all three of these things work the same way. All three of them create C-1 binary submodels to predict the logit or the probit of the response in the higher category or the lower category, depending on your software. The difference is in how they form the binary submodels. And this is something, by the way, that in the generalized linear modeling class that I started last spring, which will be coming back in a year or two, you'll get a chance to learn about these models outside of latent trait land. So that's where I'm pulling some of the same material from. So we're relying on the idea of a continuous underlying item response still as the distinction between logit and probit. So if you think that the underlying continuous response that gave rise to your categorical options has a logistic distribution with a variance of 3.29, that's your logit link. If you think the continuous underlying response has a normal distribution with a variance of 1, that is a probit link. Which of those you can use depends on what you choose for estimation. If you choose full information, marginal maximum likelihood, the thing with the rectangling, with the quadrature points, that comes in either logit or probit scaling. Whereas if you choose limited information estimation, the WLSMV diagonally weighted least squares, where you start with a polychoric or tetrachoric correlation matrix and then fit the CFA to that matrix as a summary, that only comes in probit flavor. So that's why I'm continuing to emphasize these differences in scaling, because that is going to correspond to what you get, whether you like it or not, in different methods of estimation. So the graded response model, the thing that I am expecting that most of you are going to fit in homework 5, the thing that you get a chance to practice in the last part of homework 4, is a model for ordinal data. You can have as many categories as you want, although I think M+ cuts you off after about 10. So there's at least one of you who has an ordinal item where there's 10 categories, and I can't remember which one of you it is. I apologize. But for that person, let me know if you need help overcoming limitations. You may end up having to collapse categories to get around that restriction. The idea of the binary submodels here. So if I have 4 response options, that takes 3 binary submodels. If I had 5 response options, it would take 4 binary submodels. And in each of the binary submodels, all of the responses get used. So these models are relatively low in data restriction because if there's not a lot of people in one category, the idea that you're combining across categories can compensate for that. So for instance, if there's not a lot of people who picked a 1, then 0 and 1 get lumped together in this binary submodel, and 0, 1, and 2 get lumped together here. So you can't tell as directly that there's not as many people with a 1. So it's easier to work with sparse data. Very extreme cases, you may end up having to collapse categories, but that's usually not necessary. So the model is going to think of each of these, the lower of these binary models, the part that's colored red, is considered the 0 in the predictive equations, and the part that's colored green, the upper, after the verses, is considered the 1. So everything that you learned about binary responses fits exactly the same here with that additional twist. When we say, for instance, that the item difficulty is the trait needed to get to where there is a 50.5 probability of a 1 translates to the green part. So the difficulty of the first submodel is the trait needed to get to 1, 2, or 3. The difficulty of the second submodel is the trait needed to get to 2 or 3. And the difficulty of the third submodel is the trait needed to get to 3. And M+ lists each of the different thresholds for these submodels with $signs after them in the order in which they appear in the data. So the model looks like this. So I'm on slide 9. The upper part of the slide has the IRT parameterization of the graded response model. So this model, as it was originally invented, is what I would call a 2PL-ish model, meaning that the default version of this assumes that each item needs a different slope. So that's why in the equations here, I've got an A sub I. So item 1 gets its own slope, item 2 gets its own slope, item 3 gets its own slope. But across the binary submodels, it's the same A. So the effect of theta in predicting 0 versus 1, 2, 3 is constrained to be the same effect of theta in predicting 0, 1 versus 2, 3, and the same in predicting 0 versus 1, 2, 3. So it's the same slope across submodels. That's what's known as proportional odds in the non-latent trait versions of these models. And I do not know of any version of commercial software that allows you to break that assumption. I think you'd have to program it yourself using something like NL mixed in SAS or JAGS, something to where you could write out your own model and your own likelihood function to be able to break that. It would take a lot more data too. Each submodel, though, does get its own B. So these B's, unlike the models that will come after them, are interpreted in the exact same way that the B's are in binary data. It's the trait level needed to get to a 50-50 probability. What it's the 50-50 probability of depends on which submodel you're in. So B1 is the trait needed to get from 0 to something greater than 0. B2 is the trait needed to get to 2 or 3. And B3 is the trait needed to get to 3. So if you're directly predicting logits or probits, it looks like this simplification of A times theta minus B. If you're predicting probability, then we have the e to the logit over 1 plus e to the logit. So this is the link version on the left. The inverse link version is given on the right. Logit scale on the left, probability scale on the right. So if I had, say, 5 options, how many B's do I need? 4. If I had 6 options, how many B's do I need? 5. I just gave you 6. Apparently I need more caffeine today. So this is why, circling back to the question about 10 minutes ago, if you have an item that has 5 categories and you have another item that also measures the same trait with 6 categories, it's fine. The first item gets 4 B's and the second item gets 5 B's. No biggie. If you had an item that is supposed to have 4 categories and it only has 3, for instance, then you only get 2 B's instead of 3. So each item gets its own set of parameters. That way we're not necessarily saying anything about how that item's parameters compare to those of other items. Each item can get whatever B's it wants. And that also means that the response options don't have to be of the same kind. So in addition to having 5 options versus 6 be totally fine, you can have an item where 0 is rarely and 1 is sometimes and 2 is often, and another item in that same trait where it's strongly agree, neutral, and so forth. Because there's no implied relationship across the items in what B1 means. It's just the first transition point of lower versus something higher than lower, whatever that is. So you have to know, as the architect of the scale, what the scale choices are and therefore what the B's mean. but mathematically they don't care what the options are. They just need to know that they're ordered, and that's it. Okay, how are we doing? Good with this? Okay, so it's just like binary models again on crack. Just a higher level of complexity. Same exact idea. So predictions of the model are shown on slide 10. So this is showing a different submodel as each of these curves. So the pink one describes the transition of 0 versus greater than 0. That happens at a trait level of 2. That's the difficulty. The yellow one describes the transition of 0, 1 versus 2, 3. That happens at a trait level of 0. And the last one describes 0, 1, 2 versus 3. And these curves are parallel because they all share the same A. So these are predictions of the submodels within an item. That's why A is the same. Each item can have a different A, though, in the graded response model.
Can I clarify something about that?
Please.
So is the equal A's that saying that the transition between the categories, like the difference between someone who chooses a 0 versus a 1 versus a 2, like is it saying that that difference is all the same? I know technically I think it's like the relationship between the 0 to the trait and the 1 to the trait, but is it also saying something about the transition from 0 to 1 and 1 to 2?
It is not also saying that.
Okay.
So it is describing the slope of the regression line, basically, of theta in predicting a response. And the slope of theta in predicting a response is the same no matter which response you're predicting.
Right. Okay. Would it be I guess it'd be the difficulties then, that like if the difference from one B to the next B.
Yes. So
Okay.
this picture makes it look like what you're saying because the
Gotcha.
values that I picked happen to be equidistant, but there's no guarantee that that would happen.
Okay, cool.
Let me fast forward a couple slides here to this one. This is slide 14. We looked at this before, but it speaks directly to your question. The bottom of this picture, the orange and the green and the blue dots on these lines, these are the difficulty values that correspond to the different submodels. So the choices that we have here, this is a 4-option set of items. Never, seldom, sometimes, and often are the choices. And so blue corresponds to the trait level needed to go from something greater than never. So 0 versus 1, 2, 3. Green corresponds to the trait needed to go from never, seldom versus sometimes, often. So something greater than seldom. And orange is something greater than sometimes, which is often. And if you look across these items, the distances between the orange, the green, and the blue are not all the same. So within an item, they're not equidistant, and across items, the distances between these are not the same. So the jump of like how much trait it takes to sort of jump over sometimes and into often depends on which question it is. Yeah, I have sort of like a mental image of somebody running like the 100-meter hurdles, like going through this, right? I got to jump over seldom and then keep running and then jump over sometimes and then I get up to often, something like that. The hurdles are equidistant, at least they're supposed to be, because that's the only way that you could keep track of how many steps you take in between. 3 steps, go, 3 steps, go. Unless you're short and slow like me, in which case it's like 10 steps, jump. But in this case, no, they're not equidistant. And so each of these items has an orange, a green, and a blue. Those are the 3 difficulty values, but there's only one A. So the red bars in the top are showing what A is for that whole item. A is the change in the logit for a 1-unit change in theta. It doesn't matter what it's the logit of, right? It's just the logit because it could be going from greater than never, greater than seldom, or greater than sometimes. A is the same for all 3. Okay. Do you remember the other point that I was trying to make with this picture from before? how the location of these B values directly speaks to what reliability is going to look like. The problem with this instrument is that although the blue ones span pretty low on the trait, so up to like 5 standard deviations below the mean, and the green ones are sort of low, but like within -1 standard deviation or -2, the oranges top out at about a trait level of 1. So there's no response option for people who are super high on these traits to pick. It stops it often. And that's why the fact that these oranges stop at a trait level of about 1 is directly why the test information function, so here's it in the reliability metric. So reliability is information divided by information plus 1. I have highlighted a reliability cutoff of 0.8 is what conventionally good would be, and reliability tanks after a trait level of about 0 because there's nothing for people who are up high to choose. So an easy way to fix that would be to extend the scale to add something past often. And almost always, or something like that, would allow people to differentiate themselves on the upper end of the scale, and that would get this information function to get back up higher for longer. Those of you who have, say, 7-point scales, one of the things that you'll want to pay attention to in homework 5 is to what extent these difficulty values are actually separable. Can people reliably use all the different points on the scale, or are they kind of bunched up together? If they're bunched up together, that suggests that people are not using all of the categories in the way that you had intended, and maybe you could get by with fewer. Because you start to get to the point where these labels are semantically the same. Like if I had an option for rarely, is rarely more or less than seldom? You could say that seldom is 1 and rarely is 2, or you could put them the other way, but if people don't reliably differentiate the way that you want them to, that can show up as difficulties that are all packed together. So we don't want that. You want to give people as many options as they need to differentiate themselves, but no more. And it will take pilot data and probably multiple tries with multiple samples before you're able to figure out exactly how many that is. All right, so yes, these cumulative curves, if you take the differences between them, they give you directly the probability of each response as a function of the trait. And so then you can see at a given trait level, what is the most likely answer, and ideally, each of the curves would be most likely at some point on the trait. So you'll get a chance to answer questions about these sorts of curves as well in your homework. Okay, how are we doing? Questions, clarifications? Do you want to see how to do this in M+? Yeah? Why not? All right, that's a good place to stop out of the PowerPoints. And let's look at example 6a. So I am using the same data that I did in example 5, except that it's a different response format available for the binary items. So previously we had a scale that was whether or not people could do each item. It was also administered with a slightly different wording of the question, where I have my 7 activities of daily living, and the choices are 0 can't do it, 1 is I have big problems doing it, 2 is some problems doing it, and 3 is can do it. So we're trying to sort of sort out the differences between levels of ability here with a little more fine-grained response option. So these are still 635 older adults, both men and women. We will get a chance to see to what extent the item parameters differ by gender in this sample later on, but for now we're lumping the men and women together. So here's the syntax on the left for the traditional graded response model. Let me blow this up a little bit so that we can see that a little better. So I am starting with full information maximum likelihood as my estimation method. That is selected right here under the analysis. So regular flavor ML, link equals logit for the scaling. The magic line that makes this an ordinal model is right here. That's the one thing that you need to change for sure relative to your previous homework. Categorical equals. So if you list variables on this line, they are either binary or they'll be treated as ordinal. The code is different for the other types of data analyses. It figures out automatically how many categories are in each item and therefore how many different submodels you need. So you don't have to do or say anything for it to figure this out. So I've got 7 items. I am asking for residual analysis and Tech 10. That's how we do local fit in marginal maximum likelihood. It's a giant pain in the ass because what it returns to you is a series of chi-square tables for each pair of items. So it's a lot of stuff to look through. I will show you the limited information version of estimating these models in which fit is a lot easier to assess in just a bit. I'm asking it to save factor scores. You don't have to do this, but I'm going to use these to illustrate the impact of what the item parameters are going to become on the trait levels that I'm able to get, and asking for all different kinds of plots. If you have problems with this in running this in M+, please let me know and I will help you try and troubleshoot. In terms of the code, this first line right here, IADL, that's the name of my trait. That's my predictor. I have 7 ordinal outcomes that are measuring my trait. Note that I am using the abbreviation syntax. So CIA, the categorical version of instrumental activities of daily living, that's what CIA means to me, dash CIA 7. So it's going to interpolate that when I write 1 to 7, I mean 1, 2, 3, 4, 5, 6, and 7. The star afterwards is necessary to make it so that the first loading for item 1 is free, is estimated rather than fixed to 1, because I don't want it to be fixed as a marker item in the scaling. I want to instead fix the mean and variance of my trait. So this code is going to look a little bit different than what we had before because I am going to be using the item parameters in linear combinations to generate the IRT versions of them. So this right here, L underscore I1 to L underscore I7, those are labels. They are not constraints because 1 to 7 means I am generating 7 separate labels with this one statement and I have 7 different item loadings. So the first loading will be called L underscore I1, the second loading will be called L underscore I2, and so forth. These are my thresholds. So I have $1, $2, $3. Those correspond to the binary submodels. So given my item responses, 0, 1, 2, 3, $1 gives me the threshold of going from 0 versus 1, 2, 3. $2 is 0, 1 versus 2, 3. And $3 is 0, 1, 2 versus 3. And each item has one of these thresholds for each of its binary submodels. So I'm writing this in a way that it's interpolating across items. So $1 to $1 means the first binary submodel for items 1 to 7. That's what that phrase is referring to. $2 to $2 means the second threshold for items 1 to 7. And so that's what the labels here correspond. I'm using T to stand for threshold. So each item has 3 thresholds, one in the first line, one in the second line, and one in the third line. Okay, does that code make sense to you? Nope, I'm seeing people giving me like, not really. Okay, so the reason that there's 3 lines is because I have 3 submodels. So the 3 separate lines correspond to, let me get the pictures back here, one second. The 3 separate lines correspond to these 3 separate equations on slide 9. So what M plus is calling $sign are my thresholds. Threshold 1, threshold 2, threshold 3 is $1, $2, $3. So is the first line, so the first line is all the first submodels for all 7 of the items? Yes. So the first line is referring to the first submodel for all 7 items. That's why it's $1 to $1. So it's interpolating over the 1 to 7 part. Likewise, the second line is for all 7 items. It's the second threshold for all 7 items. And the third is the third threshold for all 7 items. Okay, does that make it a little better? So here's what I'm going to tell you. In your homework, don't write these. Okay, is everybody listening? Don't type this. Do you know why? Because this works so long as everybody answered every option. In your homework, you have 24 items, and several of them didn't have anybody pick a 6. So if you try to write 5 submodels for all 24 items, M plus is going to yell at you. And it's going to say something like, I can't do this threshold. What are you talking about? And it will not be an error message that is obvious at what it means. But it's going to tell you basically, this item doesn't have 5 thresholds. And you asked me to give it 5, but I can't give you 5. So don't do this. The reason that I am writing them out is so that I can show you how to use these labels to translate these thresholds into difficulties. In your homework, I'm only asking you to translate maybe 1 or 2 of the thresholds into difficulties, and so you can write out just those thresholds and label them so that you can do math on them, but you don't have to list them all. Because M plus would do exactly the same thing if I have what I have here versus if I did this. Okay, they're all estimated by default. You don't have to type them all. The only reason I type them is to be able to label them for them to be used in equations to be converted from thresholds to difficulties. That's why I type them, so you don't have to write them. Okay? So if you do not type them out, M plus will automatically know if someone did or did not respond a certain way. Yeah, it has your data file. It figures out how many thresholds that you need and estimates the ones that you need. Now that actually brings up a good point. Let me pull up Excel here. So if you have an item that is scored, say 0, 1, 2, 3, like I have, it's going to estimate your first threshold is this one, your second threshold is this one, and your last one as this one. There we go. One, two, three. You will always see 1, 2, 3 regardless of what your answers are. So yes, you only have to write it out for the ones that you want difficulties. Now, what if your items were originally scored something like 1, 2, 3, 4? You will still get 1, 2, 3. It orders them. Your original items could be something like 15, 16, 17, 18. You will still get 1, 2, 3. Now, what if, let's say that we have a 6-point response scale. So what we should have is something that looks like this. What if nobody answered 5? If nobody answered 5, it doesn't know where the last threshold could be because it doesn't have any data to estimate it. So all you'll get is 1 to 4. Likewise, and this is where it gets tricky. Let's say that your original is 0, 1, 2, 3, 4, 5, but nobody answered 0. Then do you know what it does? Does that. So what that means, we put a 0 in here in parentheses. No, I want parentheses. There, no 0. There, I win, Excel. So what threshold 1 means for this item that has a 0 is different than what threshold 1 means for this item that does not. So yes, it will estimate as many thresholds as is needed, but you're going to have to do some detective work, if any are missing, to make sure that you know what each one actually refers to. Even worse, what if you were in a situation where nobody answered 2? That could happen, right? What you end up with is this. The first one, the second one, the third one. That's what $123 means. It's up to you to know what the first one could mean and whether you have the data to make it what it actually means.
So for that one, do you want to move the dollar sign to the next to first? I mean, next to the 1?
Yeah, we'll put
No?
that there. Thank you. I'm getting a little cut and paste happy here. Yeah, there. That's what it would look like. So it will be helpful to you to have like a frequency table or something next to you to see which ones were actually answered. That way you can label these correctly as to what $1 means in the context of that item's possible responses and which ones were actually observed. Is there a minimum number of people that it has to have a certain response or responses? As long as there's 1, it will try. If there's not enough information to estimate it, it will still try, but it may give you crazy estimates. Like it'll give you your estimate, but then the standard error will be like 20,000,007. So if you see crazy standard errors, that means it tried and failed, but it doesn't want to admit defeat, and so it still gave you the answers. So be careful with the thresholds. You have to know which options were actually observed to know what they mean. M+ doesn't care. It's like, here's your first one, here's your second one. Okay, questions on that? You get all the ones that are possible to be estimated. That is what you get. What if I label everything but no one answered 2? It doesn't care what you labeled everything. If you try to label a threshold that is not estimable in the data, it will throw an error message and it won't estimate your model. Because if you asked for a parameter that you can't have, it can't come up with the solution. So that's why I'm saying don't write them all out, because you would have to go in and customize this list to know exactly how many thresholds you need for each of the items. So for 24 items that are measured on a 6-point scale, if I remember correctly, so somewhere between 24 times 5, like that's as many as you could have, that's a lot of typing. So don't do that to yourself. You don't need to. Only write out the ones that you might want to label. Okay. This is the part that you need. The loadings. What items load on what traits and whether or not you want each loading to be estimated or not. That's what you need to tell it. Okay. The last part here, this is different than usual. I am, as it looks like from this code, it looks like I'm going to be estimating the factors mean and variance because I have stars here. I did that so that you could label them to use these in the math that follows. But I'm not actually going to be estimating them. I'm going to fix them to 0 and 1 elsewhere in the code. It's one of those funky things you have to do to make it do math with those values. They have to be something that it looks like is estimated. Question, if I code what I want to estimate, the threshold, do I get another threshold too, or do I only get that one? It's going to give you all the thresholds by default. The question is whether or not there are labels attached to them. You only need to attach labels if you want to use the estimated thresholds in subsequent functions. So what I'm about to show you, for instance, is going to do the math that converts these thresholds into B's. If you want to convert your thresholds into B's using M+, you have to do it via model constraint because it doesn't do it for you the way it did in binary data. And you could get out your calculator or Excel and do it yourself outside of M+, but then you don't get standard errors. So that's why I'm doing it this way. So if you typed out the middle line, it would do all three, but you only have one labeled line. Yes. It will do all of them regardless, unless you actively shut them off somehow. The question is how many of them have labels that you can then refer to do math on later. So let me show you where the labels come in. At the top of the next column, this is doing math using my estimated loadings and my estimated thresholds. Let me pull up as a reminder where this is coming from. In lecture 5, there is, actually, let me pull up. I've got a faster version that will open. 1 second here. This is actually lecture 7, but it has the same slide in it. One second, picture. This is a preview of next week. That's what you're getting here. Foreshadowing, as it were. This page. So this is in lecture 5. It's not in lecture 6, but it comes back in lecture 7 to remind you how these things correspond. So if I have a loading, I can get an A out of that, or vice versa. So I'm going to be going from IFA to IRT. If I have a loading, I only need to know what theta variance is to turn that into an A. If I have a threshold, I need to know what the loading is, the theta mean, and the theta variance to turn that into a B. So I am doing model constraint lines to do these two equations right here to get A's and B's. That's what I'm doing. So first thing is to fill in the 0 and 1 that I want my factor to have for its mean and variance. That allows me to refer to the mean and variance in the equations that follow but actually have them constrained like they're supposed to be. So I am identifying my model by fixing the trait mean to 0 and the trait variance to 1, same as usual. I'm just doing it here rather than over here so that I can use the factor mean and the factor variance in the equations to convert the loadings to A's and the thresholds to B's. Next line. I am creating all of my new parameters. So A underscore item 1 dash A underscore item 7. I am creating like empty columns, one per item for what the A's are going to be. Likewise, here are the 7 B's across items for submodel 1. Here are the 7 B's for submodel 2 across items. And here are the 7 items submodel 3B's. Then there is a loop option that you can use, this do thing. So it says do from 1 to 7, where you use this thing right here that is either a hashtag or a pound sign, depending on how old you are. And it writes 1 to 7. So it's writing out 7 lines of code, each time swapping out the number. So the first time through, these dollar signs are going to be 1s. The second time through, they're going to be 2s, then 3s, then 4s, all the way up to 7. So this is a loop. Starts at 1, ends at 7. Question. Can you explain why you did not make factor means and variance on the previous model section? Yes, I can. It's a quirk of M+. So because the equations to convert loadings to A's and thresholds to B's have the theta mean and variance in them, I wanted to give you code that would be versatile enough to work in the event that these were estimated as something other than 0 or 1. So I'm including the theta mean and the theta variance as part of these statements. In case they're estimated as something else, you can use the same code. However, if you directly try to fix it, so if I did this like at 0 like normal for the theta mean, and if I did this at 1 like normal, it throws an error. M+ doesn't let you label parameters that are already fixed. It only lets you label parameters that are estimated. So I am temporarily pretending that these things are estimated by putting the stars here and fixing that problem under model constraint so that the model is actually estimated. The trait mean is fixed to 0 and the trait variance is fixed to 1. But now I can refer to factor mean and factor variance in the equations like I need to go from loadings to A's and thresholds to B's. So this line right here gets me my 7 A's. This line right here gets me the B's for the first submodel across all 7 items. This gets me the B's for the second submodel across all 7 items. And this gets me the B's for the third submodel. So once again, recapping, the only reason that I wrote out the thresholds is so that I could label them. The only reason that I needed to label them is to be able to use them to compute B values in model constraint over here. If you don't need to compute B values, you don't need to label them, and if you don't need to label them, you don't need to write them out. All right, questions on that setup?
If I had a situation where like I needed to there was an item that didn't have responses or yeah, would I still wanted to calculate difficulties and or A's and B's, would I have to do that in like Excel or something? Like there's no way to do that in M+.
You can do it, you just have to change the code. So for instance, let's say that I was missing the last threshold for item 4, but I had it for all the others. Then what I would need to do is to shorten my list here to 3, CIA 5, $3, like that. So this is item 1 to 3. This is item 5, 6, 7, skipping over 4. So if item 4 doesn't have one, I don't reference it. And then I would have to
Okay.
change the labels to match.
Sorry if you said that. Thanks. That
No,
makes
I
sense.
hadn't said that. So then I would do something like third threshold for item up to 3 and third threshold for item 5, like that. And then over here, I would have to change it so rather than looping from 1 to 7, I loop from 1 to 3, and then I loop from 5 to 7. So I'd skip 4. And I'd have to change the B value list to go from 1 to 3 and 5 to 7. So it just works out to be more code because you have to manually skip the sections that don't exist in your data. All right, other questions on the setup here. So this is one model. This is what's known colloquially as the graded response model, where each item gets its own A/loading. I can compare that to a constrained version of the model, which would be like a Roche version of this model. It doesn't have a special name, as far as I know of. I just think of it as a constrained graded response model, where I am constraining all the loadings to be equal by putting this L in parenthesis. So on the right-hand side of the page, I'm referring to the 7 loadings with one name, and that is making a constraint and a label simultaneously. So just having one L means I am forcing all 7 loadings to share one number. And the reason that I'm doing this is to emphasize how flexible this modeling framework is. So there's one of the reasons why I chose M+ as opposed to the 18,000 other ways there are to estimate these models is because M+ doesn't force you to fit yourself into one type of model for all items versus another. So this framework, for instance, I've got like a 2PL version of the model where all the items get different slopes versus a 1PL version of the model where all the items share a slope. But you could see how you could compromise, right? So what if I wanted to fit a model where it looks like the only item that needs a different slope is number 7? Could I do that? It doesn't have a special name, and you wouldn't find it in FlexMert as a special name or proc IRT or any of the other things, but I could do that. So what if I wanted to have items 1 through 6 share a slope? And I want item 7 to have a different one. A7 star, like that. Question, you can't do that on other packages. The old school IRT packages that I learned first, all of the items had to be treated the same way. So if you fit, say, a 2PL model, that held for all the items versus a 1PL model. You can fit whatever you feel like with these combinations of constraints for some items and not others. So for instance, this version of the code would fit a separate loading for item 7 than it fits for items 1 to 6. You can do whatever you want. And nested model comparisons can tell you whether or not adding parameters helps or whether taking away parameters hurts. So this switch to constraining the 7 loadings to be equal is the only thing that made these models different. And so we can do a likelihood ratio test to compare their fit to decide whether or not that constraint is useful. So let me undo what I did here. Otherwise, I'll hit save and then I'll open this handout again in 2 years and go, what was I doing? Like, was I drunk and trying to make handouts? Like, what is this? Like, no, this is what happens when Lisa tries to get creative. All right. So here's my comparison of the two models. On the left-hand side is the fit of the model where there's different slopes across items, and on the right-hand side is the fit of the 1PL where all the slopes are constrained the same. Twice the difference in my log likelihoods is the fit. So likelihood ratio test of the conventional type. That is done at the bottom of the page for you. The difference is 135 on 6 degrees of freedom. So yeah, it looks like the 2PL model fits better. Each item wants a different slope. And this is all you get for fit. So at this point, we have no idea if this model fits in an absolute sense, if the model is consistent with the idea that these 7 items measure the same trait. We have no idea yet. All we know is that the model that allows a separate slope, a separate A for each item, fits better than a model that does not. So here are our results. Starting with the left-hand side. This is the stuff that M+ gives you by default, minus the labels. So this is your tuition dollars at work, me adding the definitions of what these things are up here. So what you would get on your output, for instance, is just IADL by. The keyword by should remind you that these are factor loadings. So what is a factor loading? It is a change in y for a 1 unit change in x. It is a slope. What is x? The trait. What is y? The item response. And so note that there is only one slope for each item. So the loading for item 1 is 6.8. That means for a 1 unit change in the trait, the logit of answering 0 versus 1, 2, 3, or 0, 1 versus 2, 3, or 0, 1, 2 versus 3, any of the 3 of those, if theta goes up by 1, that logit goes up by 6.8. So it's the same slope because the loading on slide 9 here is the same across the submodels. So 6.8 for item 1 is the factor loading in each of these 3 equations. And it's in logits. That's partly why the numbers are so big. So 6.8, for instance, looks like it's the highest item in terms of the loadings. Does that mean it's the best item? Trick question, right? Best for whom? Because the loading is at the difficulty point, right? It's discriminating for people in that region of the trait. That's the slope for them. So we have to dig a little deeper to know for whom is this a good item. So here are my thresholds for item 1. I've bolded them. Minus 9.8, minus 6.4, minus 1.2. This is the logit of the lower category in each of the submodels. So the logit of getting 0 instead of 1, 2, 3, the logit of getting 1 or 2, 0, 1 instead of 2, 3, or the logit of getting 0, 1, 2 instead of 3, when theta is 0. So these are thresholds. What do I need to do to turn them into intercepts? Do you remember? Yeah, this is a sign language one. Multiply by minus 1. Does anyone speak sign language? Can I get an acceptance? Can we do this as a minus 1? Okay, I'm inventing sign language as we speak here. Yeah. So if I take each of these numbers and multiply them by minus 1, I turn them into intercepts. then it's the logit of the higher category when theta is 0. But none of these tell me where the item is best. These tell me what to expect for an average person. So in my opinion, these are much less useful as descriptions of location because I don't need to know what happens for the average person. I want to know for whom are these items useful. So to get to that, I go over to the extra parameters that I asked for, which are in a different order than the thresholds because of the way that I wrote the code, but I bolded them so that we can look at them. So these are the B values that correspond to those 3 thresholds. So the first B value from item 1 is the trait needed to go from can't do it to at least can do it a little bit, right? Big problems or better. So the trait needed to go from 0 up to 1, 2, 3. That happens at a theta of minus 1.4. To be able to go from big problems doing it to some problems doing it, to go from 0, 1 over to 2, 3, that happens at a trait level of minus 0.9. And the last submodel to go from some problems doing it up to no problems. So to get from 0, 1, 2 up to 3, that happens at a trait level of minus 0.18. So on the whole, this item is useful for people ranging from a theta of about like minus 1.5 up to about 0. Those are the people that have answers in their regions. This item is not going to be helpful for anybody with a trait score above 0 because those people can do this item. I think this item is housework, if I remember correctly, item number 1. So to me, the extra trouble that it takes to get these Bs is worth it in terms of interpretation. In terms of reporting this model, though, you have a choice. And which one is going to be more palatable to the reviewers and readers depends on where you're coming from. For those of you in educational settings, you did a graded response model with A's and B's. Yay for you. For those of you from psychology or places where people are used to SEM, you have loadings and intercepts or thresholds. Yay for you. So how you talk about it is nuanced by who you're talking to, but either way, I still like the difficulties better than the thresholds. How do I explain the trait score? I feel like people would have a hard time understanding what a trait score is because it's ambiguous. Is there any way to make it unambiguous? No. It's latent. It doesn't exist. The only thing you can do is run a really effective marketing campaign to explain what a good trait score is. So for instance, when I took the GRE, it was scaled from 200 to 800. And so if I told you that I got an 800 on my GRE quant score, then anyone who took the GRE that year would be like, good for you. That didn't happen, by the way. I'm just making shit up right now. But there was a marketing campaign where if you said, or I got a 1600 on my SATs, right? People know what that means. For those of you who went to high school in the Midwest, Midwesterners up top, I'm expecting all the black boxes to raise their hands, and it's not happening. Yeah, people who took the ACT, that's where I'm going, right? If I told you that I got a 36 on my ACT, you'd be like, wow, you're a genius. That also did not happen, by the way. But the only reason we know what those numbers mean is because of the marketing behind the tests. So you will see trait scores like Roche scores in popular tests that have these arbitrary metrics, but they're no longer arbitrary because people have just accepted them. It's no different than any of the other testing situations because the trait is latent and I can give it whatever scale I feel like. Question: does starting from the constrained version of the GRM and adding parameters result in the same minus 2 log likelihood that would be obtained if we started from the unconstrained and then constrained the loadings? Yes. I think if I understood that question, the answer is yes. So let me do this tab in my Excel spreadsheet. Here's the model comparison. So I could explain this comparison from two different perspectives. It differs between which one I'm starting at. I could say that I started with a constrained model where all of the items shared the same slope loading, and I made the model better by letting the loadings differ, significantly better. Or I could say I started with a model in which all of the loadings were separate, and just to make sure that that was what was needed, I tested it against a reduced model where they were the same, and the reduced model fit worse. So you can talk about it either way. Does that answer the question? Well, thank you is the reply. So I'm going to go ahead and say yes. All right, so we're about out of time for today. Other questions before we wrap things up? All right, then go out, be safe, be sane, and come back on Thursday to hear more about this and other versions of categorical data. So, peace out, y'all.